Organic chemistry has been labeled a difficult and confusing field of study, probably because a lot of test questions here look very different from what we were used to get in general chemistry. Some students find the memorization work needed in this class to be difficult, but a lot of these difficulties can actually be remedied by reinforcing our mastery of some general chemistry topics. So, if you're studying to be a chemist, a doctor, or an allied medical professional, or you just find yourself in a career path that requires you to take an organic chemistry course, here are 8 general chemistry concepts that you must review before taking on organic chemistry. Number 1. Chemical bonding. You probably know that the two basic bonding types are ionic and covalent. You also probably remember that ionic bonding usually occurs between a metal and a nonmetal, and that covalent bonding occurs among several nonmetal elements. While these are all correct, it would be better if we review how exactly atoms use their valence electrons to bond with each other. For ionic compounds, they achieve this by having one atom donate electrons to the other, while in covalent compounds, they achieve this by making atoms share electrons by pairing their magnetic fields to form covalent bonds. Number 2. Lewis structures. Given that all organic matter consists of chains of carbon atoms which are nonmetallic, it's pretty obvious that almost all of the chemical species that we will encounter in organic chemistry have covalent bonds in them. To visualize the sharing of electrons among the covalently bonded atoms, we use simplified diagrams known as Lewis structures. The Lewis structures of single atoms have dots around their letter symbols representing their valence electrons. To show the covalent bonding between two atoms, we draw vertical lines with the two electrons that will be magnetically paired. And when we draw Lewis structures, we must remember that our goal is to make sure that atoms have 8 electrons around it, except for hydrogen and boron, of course, which need 2 and 6 electrons around them respectively. Number 3. Bond polarity. Do you have an older sibling? If yes, I guess you know the struggle when you both love video games and you only have one controller. And when you're forced to share the controller, do you ever feel like your older sibling gets more playing time than you? Well, the same goes for some bonded atoms. For instance, the bonded electrons between iodine and chlorine atoms tend to spend more time with chlorine. You see, while covalent bonding can be visualized by two atoms sharing their paired electrons, the sharing isn't always fair. Atoms with a significantly higher electronegativity tend to pull the electrons closer to them than to the other atom. And that is why these atoms develop a partial negative charge. The unlucky atom that doesn't get to be close to the electrons, on the other hand, develop a partial positive charge. In such cases, the bonds develop what we call polarity, and we indicate bond polarity with an arrow like this, which points towards the negative atom in the bond. Number 4. Formal charge. The calculation of formal charges is a quick way to diagnose the type and magnitude of charge that an atom has in a given Lewis structure. The formal charge of an atom is calculated by getting the number of valence electrons minus the number of bonds that the atom has minus the number of unpaired electrons on it. For example, let's try to calculate the formal charge of the oxygen atoms in the carbonate ion. Let's keep in mind that oxygen atoms have 6 valence electrons. For this double-bonded oxygen atoms, the formal charge is calculated as 6 valence electrons minus 2 bonds minus 4 unpaired electrons, which equals 0. Meanwhile, for this single-bonded oxygen atom, the formal charge is calculated as 6 valence electrons minus 1 bond minus 6 unpaired electrons, which equals -1. The other oxygen atom's formal charge is calculated in the same way, which results in a formal charge of -1. Number 5. Resonance structures. While covalent bonds are formed by the pairing of two electrons' magnetic fields, electric repulsions among these electrons must still be considered when we are looking into the stability of molecules. This is true especially in the case of double and triple bonds, in which 4 or 6 negative charges are confined in a very small space. In some cases, this overcrowding of charges can be relieved by resonance. Take the thiocyanate ion for instance. The electrons can move around the sulfur, carbon, and nitrogen atoms in this manner such that the charges are more spread out within the molecule. Evidence for the occurrence of resonance can also be seen in the case of the ozone molecule. Despite the Lewis structures implying that the two bonds would have different lengths, both bonds are actually 127 picometers long because the double bond is actually distributed evenly among all three through resonance. In organic chemistry, resonance can be used in predicting the stability of reaction intermediates, explaining acid-base behavior, and in predicting the products of some reactions. Number 6. Vesper theory. In a nutshell, the Vesper theory can give us insight on the three-dimensional appearance of the chemical species. Starting with a molecule's Lewis structure and the different kinds of electron domains attached to a molecule's central atom, the Vesper theory can give us the shape of the molecule based on how the position of electron pairs can be optimized given the natural repulsive forces that the electrons do to each other. Concepts of the Vesper model and molecular geometry will be useful in determining molecular polarity, which can give insight to the properties of molecules. Number 7. Molecule polarity. If we examine the bond polarities in a carbon dioxide molecule and an oxygen dichloride molecule, we see that the bond polarities within the molecules point away from the central atom. While this seems to imply that these two chemicals are similar, spoiler alert, they're not, the overall effect of the electronegativities on the electrons are not the same in these two cases. When we try to examine the molecular polarity or overall polarity in the entire chemical species, we don't only look at the bond polarities. We must also consider the molecular geometries as well. By Vesper theory, carbon dioxide is a linear molecule while oxygen dichloride is V-shaped. Because of the linear orientation of the bonds of carbon dioxide, the bond polarities of the two carbon-oxygen bonds cancel each other out just like two guys of the same strength playing tug-of-war, resulting in a stalemate. This makes the electron distribution pretty much balanced within the molecule. On the other hand, the angular orientation of the bonds of oxygen dichloride does not result in the same tug-of-war stalemate or the cancellation of bond polarities like in carbon dioxide. Instead, it seems like these two bond polarities are helping each other pull the electrons away from oxygen, which results in an overall molecular polarity with the oxygen atom bearing the partial positive charge and the chlorine atoms having the partial negative charges. Now, what we just did is the approximation of a molecule's dipole moment, or the vector sum of the bond polarities. This concept is very much important in organic chemistry since a molecule's polarity tells a lot about its physical properties and how it interacts with other molecules. Number 8. Intermolecular forces. We have previously determined that carbon dioxide is nonpolar while oxygen dichloride is polar. Now, what would happen if we try to mix them with water? Like oxygen dichloride, water molecules are also polar. Oxygen dichloride will not have trouble blending in with water due to the attractive interaction of the positive and negative portions of these two molecules. Meanwhile, carbon dioxide with no discernible charge separation would not blend in so well. Water molecules would rather stick with other water molecules instead of interacting with carbon dioxide. This is the reason why carbon dioxide gas in soda containers have the tendency to escape and fizz out of the cans, as water molecules would rather stay at the bottom of the container and stay close to each other. The different kinds of intermolecular forces can tell a lot about molecules' properties and the manner in which they interact with other molecules. For instance, we can predict that ethanol has a higher boiling point than its sulfur analog ethane thiol because of strong hydrogen bonding that occurs among ethanol molecules. We can also explain the formation of the DNA double helix because of the intermolecular forces that occur between the nitrogenous bases that it has. And there you have it, 8 general chemistry concepts you must review before taking on organic chemistry. How many of these do you know by heart, and which ones do you need to work on? Please let us know what you think by commenting down below.